All right, this is chapter 13, where we are looking at variables that are different to what we've done before. This time we're looking at nominal or categorical variables, and the techniques that we've done previously won't work in the same way. If we look at this example first, entitled the political demonstration example. 300 students at University K recently attended a political demonstration. With regard to year in school, we want to know, are these students significantly different from students at this university in general? Using some sort of significance level, for example 1% or 5%, whatever you want, in this case a 1% level. So the observed frequencies are over here. So we have five categories: freshman, sophomore, junior, senior, and graduate. And out of the 300 students, we observed these frequencies. So now the question is, do we think this matches what we'd expect in general? So the percentages that we'd expect to have, the breakdown, that has to come from somewhere else, like historical information or a previously known study giving me the percentages that I would expect. So I would expect 15% to be freshmen and so on, 10% to be graduates, making up my 100% in the university. So the 300 students that attended the political demonstration, the breakdown in terms of these five categories, does it match the breakdown of the university as a whole according to these percentages? So how are we going to decide if it's close enough to the expected percentages? Of course, if I have a sample, the same issues are there, that what I observed might not be exactly the same. All right, so we want to see if the breakdown, the frequencies in our sample, fits with what we know of our population. So what can we do to start exploring this? Well, what we can essentially do is look at, in our sample, there were 30 freshmen. We expect 15% to be freshmen. So 15% of our sample size of 300 is 45. So if I just tell you there were 300 students, if I go with the expected percentages, I would expect there to be 45 freshmen and 15% sophomores, so 15% of 300 is 45 again. So I would expect the breakdown using my percentages to be 45, 45, 90, 90, and 30 graduates. So what we're going to do is we're going to compare what we observe with what we expect to see and get a number to see if that differs significantly according to our predetermined significance level. We want to see how good does my sample fit what I expect. So how are we going to do this? Well, I have this O column, which is observed, same as my observed numbers. I have the expected frequencies, which I get from the percentages that were known for my population. And now I'm going to compare 30 to 45, 20 to 45, 90 to 90, 120 to 90, 40 to 30. It looks similar, but we want a measure to say this is similar enough, or no, here's my cutoff, it's not similar enough. So the obvious thing to do is look at the difference, the observed minus the expected. And I get negative 15, negative 25, 0. The juniors were spot on. And then I get a difference of 30 and 10. So you see sometimes the observed frequency is less than the expected, giving me a negative difference. Sometimes the observed frequency is greater than the expected, giving me a positive difference. Same as at the very beginning when we looked at variance, we need to not have the positives and negative differences cancel each other out, giving me a false impression of the deviation. So what did we do? We squared it, so we're going to square it again. So we're going to square all these numbers. Now every difference, positive or negative, has a positive effect. But these numbers are in the tens to 100 for this study, for this sample. In another situation, I could deal with much larger groups of people or a different number of objects, maybe just a handful. So I don't want the scale of these numbers to really affect the numerical measure that I associate with it. So to do that, we're going to look at these squared deviations, so to speak, relative to the size of the expected frequency. So I'm going to divide it by the expected frequencies to always scale the numbers down. It's all relative to how big the numbers were. So if I work with thousands instead, I'm going to divide it and look at it relative to that scale of number. Then I'm going to add all these up, and the numerical measure, the number that I associate with how good of a fit the observed frequencies are to the expected numbers, is going to be this 32.22. Now, if we look at this from a hypothesis testing point of view, I again have a very similar structure to the steps. I have my two populations, students at the university who attend political demonstrations and just students in general. And my research hypothesis is sort of what I'm hoping for. I'm hoping that the distribution, the breakdown, the percentages that I observe is different between these two populations, that the students attending the demonstration, the breakdown isn't the same, the distribution isn't the same as students in general in the university. And then the null hypothesis is, of course, that they are the same. So I am going to look at my comparison distribution. And the distribution that we're going to use in this case is the chi-squared distribution. Now, it also has a degree of freedom, and that's going to be the number of categories minus 1. In this case, I have 5 categories, so my degrees of freedom is the number 4. Let's just take a step back and talk about the chi-squared distribution for a second. For slide number 3, if I took samples of 300 over and over and over and over and get that numerical measure and look at how those numbers range from 0 all the way up, I'm going to get this type of distribution. Depending on how many categories I have, the shape looks different. So in this case, we're over here. If I did take many samples of 300, calculate that numerical measure, the chi-squared value, based on the 5 different categories, observed versus expected, every sample will have a different observed set of numbers. I'll get this distribution that over here, those are the more common situations. So I get something in general that slopes up a little bit and turns around and has a long tail to the right. Now again, I can use my tables and look up the different cutoff values for this distribution. If I, for example, have 4 degrees of freedom and my alpha was 5%, then the cutoff value would be 9.488, meaning that if I get my sample, and my sample gives me a chi-squared observed value of more than 9.488, I'm going to count that as being significant, that it is in fact different than the expected breakdown. So in our case, we have 4 for our degrees of freedom. We were working with an alpha of 1%. So in order for me to be that much more confident that my sample does suggest a different breakdown distribution in the student sample, in the student population that attend political demonstrations, I need to get past the 13.277 point. So let's see what we have in slide 8. We observed, so my cutoff value is 13.277, and I observed from my previous calculations a 32.22. So then we can say that it is greater, so it's more extreme. The chances of me getting a sample that extreme is so rare that when I get one, I assume that it's because I can conclude with some confidence that it's because there is actually a difference, and the breakdown of students attending the demonstration is not the same as the breakdown of students in the university as a whole. So I can reject the null hypothesis. They're not the same, in favor of the research hypothesis, and conclude at a confidence level, an alpha of 1%, they are in fact different. So now let's go back to slide number 1, where we're now just going to look at some other examples, just getting me used to the process. That's a little different, but still very similar. So we have our attachment style example, where it comes from a questionnaire from students, like in a psychology class, where we observe the type of attachments. And I have only 3 categories in this case: secure, anxious, and avoidant. So these were the actual frequencies that I observed in my sample. Now, from a previous study done in 1978, the breakdown that you'd expect are these percentages. So from that, I can take my 90 sample, 50% of that is 50.4, then I expect 18 people to be anxious in my sample and 21.6 to be avoidant. How do I calculate the chi-squared statistic? I take the difference between observed and expected, square it, divide by the expected value for each category, and add them all up. Remember, the capital sigma means I add them all up. So I do that, and I get a chi-squared value that I observe from my sample as 4.45. Now let's see, what does that mean? So first of all, I would then compare that to, let me go to slide 3 here. What did I get? I just forgot it. I just looked at it, 4.45. And I had 3 categories, so that would put me in degrees of freedom 2. Now, depending on my significance level, I could compare that to these and decide, is that significant enough, or no, not really. That's sort of what I would expect in a sample, and base my hypothesis testing, my conclusion of that. So just to emphasize, how do I calculate that chi-square statistic for my goodness of fit test? How good does my sample fit what's expected? Determine the actual observed frequencies, the expected frequencies, take the difference, square them to avoid plus and minus effects, divide by the expected frequency to scale it down so that they're always the same comparable numbers, and add them all up. Alright, in the next example, in slide 6, I have a mineral Q example. So some people are exposed to this mineral Q, and I'm comparing that to the population in general. So I want to see if the distribution of people over various categories is different in the two populations. I want to see whether mineral Q has an effect of some kind, and by that I mean how the categories compare. So if I look at what are the categories that I'm going to look at, I'm going to look at anxiety disorder, alcohol or drug abuse, mood disorder, impulse control, and so on. Does the breakdown of people having these conditions differ from the population as a whole? Now I observe these numbers from previous studies. I have the percentages of what it is in the US as a whole population, so I can calculate the expected number, the number that I would expect regardless of where the people live or what they're exposed to. Now I have my degrees of freedom. I have 5 categories again, so my degrees of freedom will be 4. My chi-squared value, I calculate the difference between observed and expected, square it, divide by the expected value, the expected number, and add them up. And I get an observed chi-squared value of 8, chi-squared score of 8.84. What am I comparing that to? Well, if I'm looking at 5%, I have a cutoff. Where is that cutoff? I look it up in my table according to the degrees of freedom, 9.488. And I see my sample is 8.84. Is that significant enough? No. No, it is not. Let's run through the hypothesis testing steps. I have my degrees of freedom. My comparison distribution is the chi-square distribution. I have a cutoff of 9.488. I only observe an 8.84, so it's not more extreme than the cutoff, and I conclude that it's inconclusive. I can't reject the null hypothesis in favor of the research hypothesis. There isn't a significant difference in people exposed to this mineral Q. Alright, the other use for the chi-square test, it's similar but not exactly the same, is the test for independence. Let's do it by way of an example, the housing and children example. So young married women who have children versus those who do not have children, and either rent or own their homes. Are those two variables, are those two factors independent? Having children or not, or owning or renting a home. So I have 2 nominal variables. Doesn't matter which one you see as first. The first one has 2 categories, have children or no children, and the other one is renting or owning. So now I observe 5, 11, 20, and 4. So I wanted to see if they're related to each other, or if they're completely independent. And it doesn't matter whether you have children or not, the ratio of renting or owning a house compares the same. So I get this as my sample. So I've rented, I have people that rent, in total 25. I have people that own, in total 15. I have women that have children, in total 16. There's my breakdown. And no children, 24. So I have a total of 40 women that I sampled, young married women. So I see here from the total that have children or do not have children, that is a breakdown of 40% versus 60%. 16 out of 40 is 40%, 24 out of 40 is 60%. And these percentages are nice and round, just for the sake of a nice example. Now, what do I expect the frequencies to be if these two factors, if these two variables were independent of each other? Well, I have 25 people that rent. 40% of all the women have children. So if I take the 25 and it really didn't matter renting or owning, I expect 40% of that 25 to have children. And I expect 60% of them to not have children. If renting wasn't an issue, I just have a group of people, they behave as the same as the whole population, 40% and 60%. If I look at the group that own their house, if the two variables were completely independent, then that would behave the same as the 40-60 split. So I would expect 40% of the women that own to have children and 60% to not have children. So I get these expected numbers, 10, 6, 15, and 9. And I'm going to compare the observed frequencies, the observed numbers, to what I would expect under what will be the null hypothesis that these variables are independent. And if I get my numerical value, which is going to be a chi-squared value again, if I get something that is very significant, way out there, hinting that it's rare, if these two variables were completely independent and they weren't related in some way, didn't affect the breakdown in any way, then I wouldn't get something that extreme. So if I do, that means that they're not independent. And there's reason to believe that having children versus not affects renting or owning a house. So we make a contingency table like this. We say the observed number and then the expected number in brackets. Observed, expected, observed, expected, observed, expected. The total would obviously be the same, and the rows would be the same, giving me a total sample of 40. Now I calculate the chi-squared value the same way. Observed minus expected, square it, and divide by the expected. Add all them up, I get 11.05. Now the degrees of freedom here will be a little bit different. It's the number of columns minus 1 times the number of rows minus 1. So in this case it's 2 each, so 1 times 1 is 1. So I have a degree of freedom value of 1, which gives me the specific chi-square distribution, and I'm going to see if that is extreme enough. Well, for that I need some sort of alpha value, some sort of cutoff. So again, to sum up, I do it in a very similar way. Get the observed numbers, get the expected numbers, calculate my chi-squared value in the same way. So if I look at it as a hypothesis test, stepwise procedure, I have my two populations. Young married woman from whom renting or owning their home is independent. And I'm trying to see under population 2, if I assume there's no difference, I assume independence. Let's see how the observed compares with the expected. So my research hypothesis is that the two populations are different. I'm hoping for different. But under the null hypothesis, they're the same, meaning there's no relationship between the two variables. They're independent. So I get my chi-square distribution that I'm using as a comparison distribution with 1 degree of freedom, and I'm going to use my 5% alpha, and I have a cutoff value of 3.841, and I am observing an 11.05, so that is extreme enough to suggest that the two variables are not independent. So I reject the null hypothesis in favor of the research hypothesis and conclude that among young married women, renting or owning is not independent of having children. So I have my goodness of fit test, and I also have this test for independence, both the chi-squared test. Let's do another example. So let me just check. I think I might want the slide first. So college generation example. So there's been a study of college experience of students who were the first generation in their family to attend. These students were compared to other students who were not the first generation in their family to go to college. So now I'm going to compare students like the ones surveyed, students whose decision to drop out or stay in college their first semester is independent of whether or not they were the first generation. So it's important to get the research hypothesis. What am I hoping for? I'm hoping for the two populations to be different. I have my sample. I want to see dropping out versus staying, that variable. How does that compare to first generation or not? And are those two things independent? Or if you're first generation, does that affect your dropout rate? If you're not first generation, does that affect your dropout rate? Is there a relationship between the variables? I don't know what it is. The chi-square test is only going to say that there is one or not based on my sample. So let's go back to that and see what I observe. Well, I get these numbers, and again they're in the form observed and expected. Observed and expected, observed and expected, observed and expected. Expected comes from assuming the null hypothesis, assuming that there is independence, that they do not affect each other. The degrees of freedom again is 1, and my chi-squared value, my chi-squared statistic, observed minus expected squared over expected, add them up, and I get a 6.73. Where is the cutoff value? Well, if I use a 1%, the cutoff value is 6.635. I'm just over that, so that is significant enough to conclude that I can reject the null hypothesis. There is a difference. They are not independent. First generation students are somewhat more likely to drop out during the first semester than other students. They are not completely independent. Being a first generation student does matter. We don't know why. We don't know exactly the reason. You can do other studies to now explore this further. The chi-squared test for independence just says that there is reason to suspect that these two variables are related to one another. Lastly, we have to talk about effect size. Now, the effect size for the chi-squared test is for a 2x2 table. I have the phi coefficient calculated like this. So my chi-square statistic divided by the sample size. So for example, if I have the 2x2 table, my chi-square statistic is 11.05 and I have 40 people in my sample. I calculate that as 0.53, and I have tables that you can see in your textbook that classify it as small, medium, or large, just like we've seen before. If I have larger tables, then I'm using Cramer's phi, which is calculated a little bit differently. The chi-square statistic divided by n, and as well as the degrees of freedom of the smaller of the two variables. So for example, if I have a 4 by 3 table, chi-square statistic of 5.83, 60 people in my sample, I calculate it as 0.22, and it has a median effect size over here. I also have the other table where, depending on the effect size and the sample and degrees of freedom, I can approximate the power of the study to give me an idea of a type 2 error, same as before. And lastly, I have another table that's sometimes useful, that's sort of the reverse, to get a power of 80% at 5% alpha. What is the sample size that I need to get that? So for a small effect size, to get a power of 80%, I need a fairly large sample, depending on the degrees of freedom, depending on the categories that my variable has. And if I already have a large effect size, I don't need a very big sample to get a power of 80%. Alright, that was the chi-square test. Remember to look in the textbook for more detailed explanations. This is just the first rundown of the idea behind this chapter, and hopefully following the correct steps, the quiz and homework will make sense.